Okay, so what is that evidence I was talking about so that I can, number one, find myself a rate law equation that could help me figure out how fast I want these reactions to occur? Because think about it. If I'm in industry and I'm making a product, I'm making no money if I have a spontaneous process that's barely moving along. So we want to control the rate of reaction. We want to change the conditions so that we get the optimal amount of product per second. And that was actually one of my jobs at one point. But, so what we're going to do is, we do an experiment. And you're going to have some data. Because you can't look at an overall reaction and assume, hey, that's going to be second order, that's first order, we're done. Because you're assuming it's a one-step process. We don't know. We can't look. All we can do is look into the process through the experimental data to get some insight on whether it could be a single we can never say definite, but we can say, could this be a single step? Most likely, most reactions are multiple step. Let's hope you can envision. So let's go to the data. Now, a lot of times you can eyeball these data tables. You can eyeball them, okay? I'm going to show you first, sometimes you can't eyeball them, okay? Sometimes you can't. So I'm going to show you first how you would set this up as a college student, and then I'll show you how you can eyeball these for more quicker ways to solve them because of the time constraints that you may have. Okay, so, any case, what I'm going to do here is the following. I'm going to do, I need to give myself a lot of space, so I'm going to kind of do it up here. So I'm going to white this out, get rid of all of this. Okay, I have the power to do that. My eye juice is still on the screen, so it's kind of gross. Okay, now, hypothetical reaction, or at least hypothetical, I should say, single step. Now, I want the rate law. I know that the R is going to equal some constant that's temperature dependent times the concentrations of my reactants. It could be both, one, okay? Now, here's what I'm going to do. I'm going to look at reaction 1 versus 2. Why? Because I'm going to see B staying constant. Now, I'm going to put experiment 1 over 2. And the reason for that is I can see that 4 is double, and I like to live in numbers greater than 1. But you could do it the other way, wherever your comfort level is. So I'm going to do experiment 2 over experiment 1, or over 2. Over 1, sorry, I can speak. And I'm choosing that only because I see that this value is bigger. Okay, so in experiment 2, all right, what do I have? Well, we have the formula. We have R equals what? R, let's do it in different color because I can. R, the rate, is equal to the concentrations to some power of A times the concentrations of B to some power. We'll do X and Y. And let's do that. And of course, you have a K there. Okay? Okay. Okay, now, that makes no sense what I'm talking about. Here we go. So experiment 1. What's the rate of experiment 1? Well, I'm up 2, I'm sorry. 7.0 times 10 to the negative 5 is equal to some constant to the A. Now the A for experiment 2 is 0.4 molar. These are molarities. Now I don't know the order, so I put an X there. And for the B, it's 0.10 to the Y. Okay, experiment 1. Okay, the rate is still the same. Times 10 to the negative 5 equals a K. And experiment 1, I have 0.2 to the same X over 0.1 again to the Y. Okay, so I put this over each other, so let's put a dividing line. Not much of a straight line, but you get the point. Okay, so we can see some things happening right away. This whole thing cancels to 1. All right, you can see that, well, these are the same numbers, so this goes to 1. So 1 is equal to, now by the way, this rate law constant, okay, is the same for both of them. Okay, so that's going to be equal to of course, the same value, so k cancels. So we got 1 equals 0.40 over 0.20, which last time I checked was what? So 0.4 over 0.2, party people. Thank you for playing. 2. Okay? 2 to what? 2 to the same x. So here's my equation. 2 to the x equals 1. What must x be? 0. Okay? That is a 0 order. X equals 0. Okay? Now it's important. Now you may say, Mr. Grodsky, did all that work and I could have saw that. Yes. But sometimes you have to do this. Sometimes they're not going to give you these numbers that cancel. So if I eyeball it, okay, here's what I would say. I doubled, okay, A from 2 to 1. Keeping B constant, my rate stayed the same. It screams to you that there was no effect by doubling A. So A is 0 order. So for A, you put 0 order if you like, or you can just leave it out because that'll just be a 1 as it equals. But I'm just going to put it in there. All right? And you would do the next for the other one. Okay, now the other one, pick any one you like, keep A constant. Okay, and this, so I'm going to pick 3 and 1. So keeping A constant, as I go from 1 to 3, I double B. What happens to my number? 7.0 times 10 to the negative 5 becomes 28 times 10 to the negative 5. All right, so 2.8 times 10 to the negative 4 is the same thing as 28 times 10 to the negative 5. How is 7 and 28, how are they different? 4 times. So I doubled B. Right now I'm eyeballing. You can do this for speed, okay, but I'm doubling B, keeping A constant with respect to A. So we did this, A canceled out, and this increased 4 times. Hey, if I'm doubling something, the initial concentration and the rate increases 4 times. That's the square of the change. So that means that B is what? Is a second order. Now, do you need the A sitting there? No. You could rewrite this if you want. R is equal to some K, B to the second power. While we're on the topic, what does this scream to? Screaming now. If I find a 0 order for one of my reactants, and which is now A, what do you think that's telling me? Right, or it's in another step. That means that A has to be there for this to work. It doesn't mean you need no A. A has to be there. But changing A doesn't change it because changing A must be in the what? One of the faster steps. A is not in the rate determining step. 2B are. And this is how we start proposing a mechanism. So both B's are in the slowest step, and this A is in a step that's fast. It could be a second step, third step, 5 steps, who knows? Okay, but the point being is, this is not a one-step reaction, as most reactions are usually not. Okay? So this is screaming to me that A is not in the rate determining step. There is a mechanism here, like this, at least 2 steps, could be more. We never know exactly. All we can do is other experiments to test those proposed steps. Okay. Now, what's the order with respect to A? You would say 0. Now, before I continue, I can do the same thing for this one. Okay, and I would get, all right, 4, because this would be what? 28 over 7. You would get 4 equals what? 2 to an x. And of course, that x would be equal to 2. Okay, so you could solve for it this way. You can solve for it eyeballing it. If you don't have time, you eyeball. But there are going to be problems where this number is not, it doesn't cancel. So it means you have to do the math. Okay, so make sure you understand what I did here. Okay, it's the same thing as eyeballing. If you notice, in these problems, things are canceling, so life is easy. But if these numbers don't cancel, if you don't have, in an experiment, anything staying the same, you are forced to do this method because you're going to get a number here that you have to work with. And you'll see examples of that in your homework. All right? But a lot of problems you can just do what we just did here and eyeball it. What's the overall, with respect to B, of course, it's 2. What's the overall rate order? Well, 2 plus 0 is what? The overall reaction order is 2. It's the sum of the exponents always. Or just 2 if you want to think of it that way. Now, very important, almost every rate law question is going to want to know, hey, how do we find the rate constant? How do we find that K? Now that we found the orders from the experiment that speak to a possible mechanism, that's at least 2 steps. What is that K? Well, I have the rate, I have the concentrations, solve for K. So, pick any experiment. I'll pick the third one. It doesn't matter because K will be the same for each of them. So R is equal to K. I'm forgetting A, just going to do B squared. So, solve for K. K is equal to what? K is equal to the rate over B squared. What's the rate? The rate in your experiment is 2.8 times 10 to the negative 4. So it's 2.8 times 10 to the negative 4. That's a 10. Negative 4 over what? What's the concentration of B? 0.2, 0. Of course, that's to the seconds, so it's squared. Now, understand our units here, and you have to make sure, because normally when you solve for this, they ask for the units, so be careful. Rate is usually in molarity per second, and this is a molarity, isn't it? Right? That bracket is molarity. So, that's squared. Don't forget that because of the rate law. And now we solve for that. No big deal. So I take my handy-dandy calculator. Don't forget it on that day. 2.8, although I do have extras, of course, to the negative 4. Divide by, what's 0.2 squared? 0.04. Okay, and I get 0.007. Now they'll give you a point for the 0.007. And they'll give you a point for the right units. What are the units, my friends? Well, look over here. We have molarity per second all over molarity squared. Okay? So you can clearly see, hopefully, that this molarity will cancel with one of these. And what's going to happen is you're going to have 1 over molarity second. Now, there's another way to write that. 1 over molarity second is molarity to the negative 1. That's the inverse. Second to the negative 1. Okay? Then accept all 3 of these. Probably not the canceled one, but you got to have the right units. If you're showing off, you know your chemistry, m to the negative 1, s to the negative 1. You may say, are the units always going to be the same? No, because what if this was what if A was first order? Then you would have molarity cubed in the bottom, and this would be m to the negative 2, s to the negative 1. What if it was just a first order reaction? Then it would be just s to the negative 1. So depending upon the overall order depends upon how many molarities you have. Okay, so be careful. That's 2 points there. And then letter E, classic question. What is now the rate? My friends in chemistry, it's just not a chemistry problem. Now that we solve for the K, using one of the experiments, we use the experiment to figure out the orders. Now, having the rate law complete, having the orders and having the K, I can now predict and control my reaction. What is the rate when I have these? So we just plug them in now. Very simple. Okay, so what's the rate? R, again, is equal to the K times A to the 0, so just going to B to the squared. I don't even consider A. A is not in the rate law. So K is what? 0.007, 1 over molarity, 1 over second, times what? B squared, 0.05, that's a molar squared. Okay? So, put that in your handy dandy calculator. And making sure I do this right with my big fingers. I get the rate to be equal to, and I'll write it up top here. Where is my, oh, it's equal to 1.75 times 10 to the negative 5. Now, what's my unit? Well, what do we have? We have 1 over molarity second, that was my units for my K, times what? Well, this is molarity squared. What's going to cancel? One of the molarities. There's only one here, so you're going to get a molarity per second, which, my friends, in chemistry is a rate. How much product or how much am I going to make per second? You should always get a molarity per second for your R. Okay? So that is the essence of every single rate law equation, except you just need some practice. So you're going to do number 2 in a second by yourself. Let's go on to the back side. Another way to look at it. Okay? I have a proposed mechanism. This is a proposed mechanism of the decomposition of hydrogen peroxide. Or this, I'm sorry, in this case, this is the mechanism that they've tested. Now, knowing that this is the mechanism, let's just make some sense of this. What is the chemical equation of the entire process? Well, I'm going to cancel out intermediates, and if there's catalyst, I'll cancel those out too. What can I cancel out? What's linking one step to another elementary step? The iodide ion negative. So we're going to cancel that out. What else can I cancel out? The I negative, party people. And that is a what? What's the I negative? This was an intermediate. That's a catalyst. Now, why is it a catalyst? You explain this, people. Why is it a catalyst? Why is I negative a catalyst? Without these catalysts, would this mechanism go? No. What creates these two steps is this catalyst. H2O2 barely reacts. You guys remember the elephant's toothpaste? I had dropped a catalyst. It was I negative. It was going, but going very slow until I dropped the I negative and you saw the explosion of foam, because this created this pathway which thermodynamically is more favorable, or at least creates a lower energy cost to start the reaction. So the overall reaction is, well, 2 H2O2s, 2 hydrogen peroxides, breaking down into what? H2O, and there's 2 of them, and an oxygen. If you looked at this reaction and say, hey, it's a tiny little reaction, you just looked at it and say, hey, that's second order. What's the rate law for this process? How do I get the rate law? Which one is the rate determining step? Which one is the step that we have to wait to get out of the house? We get to where we're going as fast as that person leaves the house. This is the rate determining step. Now, this is important. If this is the rate determining step, which is the slowest, this is the step that I write my rate law from. This is where I write the rate law from. So the rate law is R equal the K, and guess what? I only have one what? H2O2. And what's the coefficient in front of that lonely H2O2? 1. See, knowing that this is actually the mechanism, and knowing it's the slowest step, that we're going backwards now. Using this information, this is to the first order. How come it's not 2? How come I don't get a 2 here? Because one of the H2O2s is in a faster step that doesn't determine the rate of reaction. Does that make sense? Okay. Identify the intermediate, if any. Of course, we just said it was I0. Why? It links one step to the other. What distinguishes an intermediate from a catalyst? Well, catalysts never get consumed, so they're reproduced. But more importantly, this is really imperative, the catalyst creates this reaction mechanism. If you add another catalyst, it creates another series of steps. It starts the process. Without this catalyst, guys, do we have this intermediate? No, therefore we don't have a second step. The catalyst creates a new pathway. Last year in Regents chemistry, said a catalyst lowers the activation energy. It does so because it creates a pathway that requires less energy to start the reaction. It creates a new mechanism. It's a better definition. Okay? So what distinguishes an intermediate from a catalyst is a catalyst does not get consumed. And it starts the process, okay? And it gets reproduced. Okay? All right, and then the next one is 4. That'll be your homework to derive the rate law. Okay, so your homework or classwork you can start now. I want you to do number 2 here. And I want you to do number 4. Key, of course, is always posted. And then I also want you to do kinetics rate law 1, wherever that might be. I want you to do the first page, 2005B. And then I want you to do 1991B. So 2005B, 1991B, those 2 questions, including all the other ones.